Assalamualaikum warahmatullahi wabarakatuh. This is the second part of the LU4, which is the introduction to organometallic chemistry. Okay, these are our learning objectives. The first one is to explain the reactions of organometallic compounds. In this part, we will learn on different types of reaction that occurred for the organometallic compounds. And for the second objective is to know the application of the organometallic compounds in various industries. Okay, the first part, which is the reactions in organometallic. The first reaction is the oxidative addition, in which the reaction involves the addition of two ligands, okay, to the metal center, and the oxidation state of the metal will be increases by 2. If you look at this general reaction here, the complex, the initial complex of metal coordinate compound, the oxidation state is 0. And after the reaction, the oxidation state has been increased by 2. And also, in terms of the electron count, from 16 has been increases to 18 after the addition of 2 ligand here. This is what we call as the oxidative addition. In oxidative addition, okay, as mentioned earlier, the coordination number, electron count all rise by 2 units. And you have to remember that the metal fragment, okay, the metal fragment of oxidation state can give an oxidation addition only if it has a stable oxidation state and can tolerate an increase in its coordination number by 2 and accept 2 more electrons. If it is stable after addition of the oxidation state, it can tolerate the increase of a coordination number by 2 and accept 2 more electrons, then the oxidative addition can be occurred. Okay, apparently the last condition of the metal fragment is 16 electron or less complex with 4 or less coordination number. You can say that, okay, the last condition of the metal fragment is 16 and with coordination number 4. Okay, whereby the reductive elimination is a reaction opposite with the oxidative reaction that has been mentioned earlier. In reductive elimination, the metal reduces its oxidation state and electron count. It's a vice versa from the oxidation addition, where you can see that the metal oxidation number decreased from 2 to 0 in this example. Then the coordination number being decreased from n plus 2 to n, where you can see that 2 of the ligand have been removed. Okay, the R and X has been removed from this reaction, which is the reactive elimination reaction. Okay, when the X is H, okay, the reaction is usually kinetically facile, favorable, and thermodynamically favorable. Okay. But then if X is equal to methyl group, the reaction is still thermodynamically favorable, but in terms of kinetic, it becomes lower. Okay, why? It is because H atom has a faster rate due to the inability of the electron that bond to the which located at the 1s orbital, meaning that the H carries no electron other than bonding electron, okay, in the s orbital. But then the CH3 there carries other electron, and making the breaking and making bond become hard. Okay, if the hydrogen atom, no electron other than bonding electron, making the breaking and making bonds in any direction in the transition state is easier. For the CH3, the sp3 orbital is directed in space, so there can often be poorer orbital overlap in the transition state. These are the example of the reductive elimination here, where 2 of the ligand being removed. and become only this complex. Okay, this complex. And this is the ligand that being removed through reductive elimination process. Next, ligand dissociation. Okay, what is a ligand dissociation? Meaning that the ligand dissociates or break down into another compound, and usually through thermally or photochemical reaction. For example, these complexes, the molybdenum being attached with the with the CP here, cyclopentadiene, and also the carbonyl group. And after being heated, okay, heated thermally, the reaction through thermal reaction, the carbonyl group being dissociated from the metal and produced or being released as the carbon monoxide gas here, leaving behind only the complex, this complex. Apart from CO ligand, the phosphine ligand, okay, the phosphine ligand with phosphorus group, is either methyl or phenyl or fluoride, okay, and so on. The ligands are the common ligands that can be dissociated from a complex. The rate of dissociation of phosphine ligand depends on the Cohn angle. Look at here, this is what we call as the Cohn angle, which has been defined by Tolman. If you look at the Cohn angle, okay, Cohn angle, the larger Cohn angle means that the faster the ligand will be dissociated. Okay, and due to the crowding effect from the ligand, okay, if you have a bigger size of R group, then it may contribute to the higher Cohn angle. If you have higher Cohn angle, means that the ligand can be easily dissociated. The table here is the list of the phosphine ligand with different Cohn angle, and obviously if you see the last compound here, phosphine compound here, has the largest Cohn angle. Therefore, the dissociation process is higher compared to the pH3 here. And the example of dissociation reaction in which these complexes acts any ligand, okay, the complex attached with 4 phosphine group, then one of the phosphine group has been dissociated, leaving behind a vacant site. Next reaction is insertion reaction, where it involves the addition of a new ligand to the metal center. Yeah, but different from the oxidation addition, the insertion process or insertion reaction doesn't give any addition to the oxidation state and coordination number to the complex, because the reaction happened in between the metal and the prior ligand attached to the metal. It through the insertion process here, so no any other addition in terms of the oxidation state and also the electron count. Okay, the addition happened in between. Now we move to the beta elimination process, where most alkyl that attach to a metal center, okay, it can be converted to a vinyl by undergoing a process what we call is a beta elimination process. Okay, for a beta elimination to be occurred, there are several points that need to be considered. The first one is that the beta carbon of the alkyl bears a hydrogen substituent. Okay, you have to make sure that there is a beta carbon with hydrogen substituent. Then they have the beta hydrogen here. And the second one is that the M metal carbon-carbon H unit has a roughly coplanar conformation. They're almost the same plane, at the same plane. Okay, there is a vacant site on the metal, which is cis to the alkyl. There need to be a vacant site for the metal on the metal, cis to the alkene. It cannot be in the position cis trans to the alkyl. This position okay, this position not okay. The reaction is much more reactive in the transition metals compared to the main group. Why? Okay, we look at it later. So this is the general reaction in which beta elimination happen. The hydrogen go to the vacant site, then the C double bond CB eliminate, leaving behind this complex and the alkene group. What we can say that the beta elimination reaction is actually the reverse reaction of olefin insertion in section 4.4.4. The term vacant site in the third point, okay, refer to an empty orbital in the metal that is ready to accept a pair of electrons from the beta carbon H bond. Okay. And this is the reason why the main group elements undergo slower beta elimination compared to the transition metal. Because the main group element, they have less ability to stabilize in transition state compared to the transition metal. Transition metal, they can stabilize themselves easily. Thus, the beta elimination can undergo very fast compared to the main group element. And these following conditions are known to stop the beta elimination. Okay. Some of the reaction or compounds cannot undergo the beta elimination because there is no beta hydrogen. If you look at here, there is no beta hydrogen in this compound, for example. Okay, no beta hydrogen. The second is alkenes for which the beta hydrogen is unable to approach the metal because of the bulky system. Okay, the size is too big, causing the hydrogen unable to approach the metal center. Thus, the beta elimination process cannot be occurred. Next is the position that is not coplanar. They are not coplanar with the metal here. Thus, unable for the hydrogen to reach the metal center. So, the beta elimination cannot be occurred. The fourth reason is because of the D0 complex. For example, the Ti here, Ti is 0 complex, so it cannot happen. The beta elimination cannot happen although they have the beta hydrogen. Although vinyl and phenyl group, okay, if you look at the vinyl group and the phenyl group, they also have beta hydrogen. But why the beta elimination cannot be occur? This is because the vinyl and phenyl group, they are sp2 hybridized carbon. So the location of the hydrogen attached to the beta carbon is much more far compared to the sp3 carbon. sp3 is about 109 degree to the metal center, but then the sp2 hybridized carbon, they are 120 degree to the metal center. Therefore, the vinyl and phenyl is not ready for the beta elimination process. For complexes with isopropyl and third butyl groups, they also cannot undergo the beta elimination because of the steric effects. The size of the third butyl and isopropyl is big, so it prevents the hydrogen of the beta carbon to reach to the metal center. And this is what happened to the Ti with a D0. Okay, D0. Okay. The beta hydrogen can actually form bond to the Ti, but it doesn't undergo beta elimination process. The alkyl is called as agostic alkyl. This is the agostic alkyl here. Okay. The reason why Ti complex doesn't undergo beta elimination. Okay, why? Because there is no electron from the Ti. Tadi kan kosong, so no electron from Ti to be back donated to the sigma pi orbital in the CH bond. It is the back donation, the electron at the Ti, okay, that can back donate is important. Okay, the ability of the electron to be back donate is important to break the CH bond in the beta elimination process. So if there is no electron for backdonated process, backdonation process. So the break of the CH bond cannot be happen for elimination beta elimination reaction process to be happen. In other words, the metal has any metal, okay, the metal which involved in beta elimination need to be a good sigma acid with an empty d orbital and p base with and pi base with and filled d orbital for beta elimination to occur. Next reaction is the cyclometallation and rearrangement, where it involves the combination of two C double bond C and C triple bond C to form a metallocycle complex. For example, here these two units of C double bond and C double bond C here will produce a metallocycle complex, and two compounds or two units of C triple bond will produce and also metallocycle with double bond here. What happened is that the C double bond C and C triple bond C are being reduced and coupled to the metal center to give a metallocycle complex. And the reduction of C double bond C and C triple bond C are known as the reductive coupling. Okay, on the other hand, the metal center being oxidized. Okay, the C double bond C here being reduced, however, the metal center being oxidized compared to its original oxidation state and is called as oxidative coupling. Okay, the compound undergo reductive coupling, whereas the metal undergo the oxidative coupling. Another way of forming metallocycle is shown below. The biphenyl iridium here, biphenyl iridium complex, is very interesting. This is the biphenyl iridium complex. This one, okay. Interesting complex where it is rare and stable in air, where the compound here being added to the iridium complex, then they will form the biphenyl iridium complex. Now, we move to the application of the coordination metal or the metal complex in the industries. The first example is the Ziegler-Natta polymerization, in which the Ziegler-Natta catalyst has been used for alkene polymerization. The well-known catalyst is the TiCl3 and ET2AlCl, where this catalyst is active at 25 degree and at 1 atm, meaning at room temperature condition. By comparing this catalyst with other catalysts and also other polymerization process, the Ziegler-Natta catalyst is have more advantage because the others, they require a 200 degree and at 1000 atm for a reaction of a polymerization to be occurred. Okay. In addition, in terms of the product produced, the product is also less branches compared to the thermal polymerization. And this is the early proposed polymerization mechanism, where it happened through the insertion process here, okay, in between Ti and the other molecules. So it happened after through the insertion process. So we take note that the reaction above assume that no beta elimination can happen due to the Ti4 plus use, which has no electron to be back donated to the alkyl chain, is what we discussed earlier. If there is no electron to be back donated, so no beta elimination process. In addition, there is no electron back bonded, so they can say that the transforming of CC to C double bond to C single bond is through insertion process. However, a pair of researchers named Green and Rooney, they proposed another mechanism, okay, where they said that the reaction is through alpha elimination via acoustic hydrogen, and then they form a metal hydride complex as shown below. Okay, after the alpha elimination, then they undergo they form a metal hydride. Okay, metal hydride. But then the many organometallic chemists, they question the mechanism because the justification of the alpha elimination is not convincing. The reason is that the alpha hydrogen is not coplanar with the metal center like the beta hydrogen. Okay, for the elimination process to be occur, they need to be in coplanar coplanar position. But then the alpha hydrogen is not coplanar. So the mechanism, the Green-Rooney mechanism, has been questioned by the organometallic chemists. Therefore, in the latest development, the most accepted mechanism for Ziegler-Natta polymerization is through the reaction below. Okay, the empty vacant orbital, addition of the ethylene group, then the rearrangement happen. After that, the migration happen. So then this the production of the polymer here. Okay, next, according to the mechanism, the Ziegler-Natta polymerization can only start with the TiCl4, LET3 and CH2. The more CH2 used, then you have a longer alkyl chain. Okay, next, the other organometallic complex that worth to mention is the Schwarz reagent, where the chemical name is iconosine chloride hydride. This is the structure for the complex. The Schwarz reagent reacts with the unsaturated linkage, for example, the alkenes and alkynes, through the cis addition of hydrogen and zirconium. And then after the reaction with the zirconium and hydrogen, okay, it will generate the organozirconium for complexes. Then to produce other functional organic molecules, the organozirconium complex is treated with the electrophiles and leads to the halides, the aldehydes or ketones, the carboxylic acid, and other functional molecules, includes the alkane. The mechanism of CC double bond isomerization with the Schwarz reagent is shown below, where it involves the reaction here, okay, to produce the organometallic. Okay, regardless of whether the statin olefin is a trans or cis olefin, the final product must be a terminal alkane. Okay. And this is very useful for the petrochemical production. Next is the Wilkinson catalyst, where it was named after the person who developed the catalyst, and the person won the Nobel Prize in 1973. The function of Wilkinson catalyst is to catalyze the hydrogenation of olefin to give an alkane. Here, this is the Wilkinson catalyst. And you can see the reaction happen where the Wilkinson catalyst being oxidized through the oxidative addition, and the RH plus 2 in terms of their coordination number from 1 to 3, and 6 plus 2 for in terms of their electron count. Then one of the ligand being removed, so now it is become 5 complex still with the RH3 here, and then the addition of the ethylene here, okay, through here, this is the insertion of ethylene. Next, after that, through the insertion process here, okay, DH, okay, and here the insertion process happen between here, this H is this, okay, ini berlaku insertion. Okay, then after that, through the reductive elimination, this is where the alkane being produced and get and only get the 3 coordinated compound, then addition of H get back to the catalyst that used. Okay, and that is all for the lecture, and the reference of this the lecture notes is taken from these 2 books, and you can look for these books to have a further reading. Okay, that's all for the lecture. Thank you very much.